Let us take few more question and answer in data structure and algorithm. Define the following terms: ADT, column major ordering of arrays, adjacent multilist, and game trees. Abstract data type, a useful tool for specifying the logical properties of data type is the abstract data type or ADT. So the data type is a collection of values and set of operation on those values. The ADT refers to the basic mathematical concept that define this data type. So ADT is not concerned with the implementation details at all. This is at the discretion of the implementer. So by specifying the mathematical and logical properties of data type or data structures, the ADT is a useful guideline for implementation or useful tool for programmers who wish to use the data type correctly. In ADT, it has two parts: the value definition and the operation definition. And the value definition defines the collection of values for ADT and consists of two parts: the definition clause and the condition clause. This is the operation definition, just an example, so you don't need to worry about it. Just some precondition, postcondition are there, and then you can implement it by yourself. It's your discretion. Then comes the column major ordering for array. Let A be a two-dimensional M into n array. That means you have m rows and n columns. So, though this A, which is an array, is pictured as a rectangular pattern in, say, rows, row 1, row 2, column 0, column 1, column 2. So this is a regular pattern with row and column. It is represented in memory by a row of m by n columns, like this, column major. So first we have 0, 0, then 1, 0, then 2, 0, then we have 0, 1, 1, 1, 2, 1, and then 0, 2, 1, 2, and 2, 2. So the elements are stored column by column, that is m elements of first column is stored in first m locations. Element of second column are stored in second. This is first m location, this is second m location. This is column major ordering for arrays. The next is, in column major order, the location will be given by base A plus W into m minus j m into j minus LBC, where m is the number of rows in the array, W is the number of bytes per storage location for any element of the array, LBC is the lower bound for row index, LBC is the lower bound for column index, LBR is the lower bound for row index. Next comes the adjacency multilist. What is adjacency multilist? In the adjacency list representation of an undirected graph, each edge Vi or Vj is represented by two entries, one on the list for Vi and other list for Vj. But in certain situation, it is necessary to be able to determine the second entry for a particular edge and mark that edge as we have already examined it, so already having been examined. So this can be accomplished easily if the adjacency lists are actually maintained as a multi-list. That is the list in which the nodes will be shared among several lists. For each edge, there will be exactly one node, but this node will be in two lists. That is, the adjacency list of each nodes, it is incident. So the node structure will become like this. This is M. This M is filled to indicate whether or not the edge has been examined. V1, V2, the linked for V1, linked for V2. Let we have this graph. So we want to make the adjacency multi-list. How we are going to make it? Let me show the graph again. So it will be something like this for this one. This graph, let me explain you one by one what is happening here. So we have vertex. How many vertices are there? 1, 2, 3, 4. 4 vertices are there. So what 4 vertices are there? These are your vertices 1, 2, 3, and 4. So these 4 vertices are like this. We have edge 1 to 2. This is the first edge. Okay, 1 to 2. How it is going to be written? This is N1, 1 to 2, and this is 1 to, say, edges 1 to 3. So 1 to 3, 1 to 4, 2 to 3, 2 to 4, 3 to 4. But what is happening here is the lists are like this: N1 to N2 to N3. So from N1 to N2 to N3, N1 to N2 to N3. For this, we know that 1, 2 also has this 1, 2 also has N2 and N4. That is, so let me explain you in some other way. Okay, this is a 1 and 2. This is 1 and 2. Now 2 is connected to 4. So 2 is connected to 4. For that we write N4. And 1 is for this edge. 1 is connected to 2. So 1 will be N2, 2 will be N4. Then for 1, 3, this 1, 3, again 1 is with 3, so this is N3, and 3 with 4, so this is N4. Then we come to N3. See, 1 to 4. 1 to 4, 1 is with 3, but this is already done. So we'll write 0 here. With 4, it is where we go to N5. Why? Because it is 2 to 4. And 5 says, this fourth one says, this is the V2, and this says N5. What does it mean? It means that we have N5, that is 2 to 4, which is not covered here. This is 2 to 4, so this is pointing to N5, which is this one, 2 to 4. Again we are coming to N4. N4 says 2 to 3, so 2 is with N5. Why? Because again 2 to 4 is given in N5. And what about 3? 3 is 1 we have taken, 4 we have taken. There is no edge from this. So N6 is 3 to 4. 1 and 3 is already been done. 3 is 4 is not done. So 3 and 4 is N6. Now 3 and 4, because 3 to the edge from 3 to 1 is already taken, 3 to 4 is already taken, and we will place 0 and 0 here. This is for 3, 4. So the vertex 1 is N1, N2, N3. Vertex 1 is N1 with N1, and then this N2 and N3, because we have edge 1 here. And vertex 2 will be N1, N4, N5. That is, this is, you can very well find from here also, and here also. Vertex 2, very good, you can find it, 2, 2, 2. So that will be N1, N4, and N5. Where is 3? 3, 3, 3. So that is N2, N4, N6. 4, 4, 4, 4. That is N3, N5, and 6. So this is how we make the adjacency multi-list. Now we come to game trees. So an interesting application of trees is the playing of games such as tic-tac-toe, chess, or there are various games, So we can picture the sequence of possible moves by means of a game tree, in which the root denotes the initial situation and the branches from the root denote the legal moves that the first player could make. At the next level down, the branches correspond to the legal move by the second player in the situation, and so on and so forth. So with branches from vertices at even levels denote move by the first player, and from vertices at odd levels denotes moves by the second player. Now we'll see the tree. This is tic-tac-toe. This is the root, and these are the various possibilities of the first player and the second player. Describe various memory allocation strategies like best fit, worst fit, and these type of strategies. So we'll see each of them in detail. Before that, let us introduce that memory allocation strategies. If it is not desirable to move blocks of allocated storage from one area of memory to another, it must be possible to reallocate memory blocks that have been freed dynamically. So each time a request is made for a storage, a free area large enough to accommodate the size requested must be allocated. And the most obvious method for keeping track of the free block is to use the linear linked list. So each free block contains a field containing the size of the block and the field containing a pointer to the next free block. So a global P for free block points to the first free block on the list. So there are several methods of selecting the free block to be used at or as when required, when the requesting storage is there. The first fit method is like this. The free list is traversed sequentially to find the first free block whose size is larger than or enough equal to amount requested. So when the block is found, it is removed from the list. So if it is greater than the amount requested, the first of these portion remains on the list and the second is allocated. Best fit method is, this method obtains the smallest free block whose size is greater than or equal to obtain such a block by traversing the entire free list. Right? We'll see which free list follows. We'll see by diagram also. Worst fit method will be, in this method the system always allocate a portion of the largest free block, largest. That is why it is worst in the memory. So the philosophy behind this method is that by using small number of a very large block repeatedly to satisfy the majority of requested, many moderately sized block will be left unfragmented. So this is free storage list. This is the first fit method. This is the start address. This is the length. So now the request for 13K has come. So 13K, first fit means it will be allocated to 16K. This, right? What about best fit? If the request is 13K and we have 5K, 14K, 16K, 30K. So 5K it will not be able to, 13K will not be able to fit. This is large enough for 5. Then we have the second one, which is 14K, and this is best fit. Why? Because 13 can be easily fit without even leaving enough space that is possible with 16 or 30. Next is the worst phase. 13K requirement has come, and we'll find that place or that memory length which wastes a lot of space. So what it will be? We'll find the difference, and the greatest difference will be allocated. So the largest is 13 minus 30. That is how much? 13 minus 30 is this is worst fit. So it will be say 17. Sorry, 13 minus 16. It will be 3. 13 minus 14. That is, you cannot allocate here, and you cannot allocate here also. So you will allocate it at 30. So at this position it is going to be allocated. How memory is freed using boundary tag method in the context of dynamic memory management? See, to remove an arbitrary block from the free list or to combine it with newly freed block without traversing the entire list, the free list must be a doubly linked list. So to each free block must contain 2 pointers, next and previous, to the next and previous free block on the free block. This is indeed needed when combining a new freed block with a free block that immediately precedes in memory. So the front of the free block must be accessible from its rear. One way to do this is to introduce a B size field at a given offset from the last location of each first free block. So this field contains the same value as the size field at the front of the block. So this field contains the some value as the size field at the front of the block. So this figure below illustrates the structure of the free. This is the free block and this is the allocated block under this method, which is called the boundary tag method. So each of the contract fields, F flag, this size, next, B size, and B flag is shown as occupying a complete word, although in practice they may be packed together. So several fields to a word. So we assume that this F flag or B flag are logical flags, and that truly indicates an allocated block, and the false indicates a free block. Okay. So using the information in the free block and the newly freed block, the system merges the two blocks into a bigger whole. This is boundary tag method to free memory. What is height balance tree? Explain how the height is balanced after deletion of nodes in it. Height balance tree is also known as AVL tree. AVL tree is a binary search tree. So AVL is BST. It is a binary search tree in which the height of the left and right subtree of the root differ by at most 1. If it has 2 or minus 2, so 0, you have to balance it. So the root differs by the left or right subtree of the root differs by at most 1, in which the left and right subtrees are again the AVL trees only. So with each node of an AVL tree is associated with a balance factor, that is left high equal or right high according. So respectively, as the left subtree has height greater than, equal to, or less than that of the right subtree. So the definition does not require that all leaves be in the same or adjacent level. For example, this is an example. To achieve balance in an AVL tree, after insertion, deletion, rotations are carried out, we need to do the balancing. So let us see what rotation means if something of this sort happens. Let R be the root of the tree and X be the root of its right subtree. This one. So right high means if the item is right high, the action needed in this is left rotation. Means left rotation. So we have rotated the node X, this X to this root, dropping R to down into the left subtree of X, the subtree which is T2 of nodes with keys between those of R and X now becomes the right subtree of R rather than the left subtree of X. Okay. Now if we have left high, so it is carried out in the similar fashion of right high case. But what about the double rotation? This case too will have it was left rotation will take the right rotation in this case, but the conditions remain the same and the result will remain the same. One on the left hand side, one on the right side. Then double rotation means in this case it is necessary to move 2 levels. You have 2 levels to the node W. Okay, that roots the left subtree of X, which is this X, to find the new root. So this process is the double rotation. Why? Because the transformation can be carried out in 2 steps. First, by rotating the subtree within root X to the right, that is right rotation. So W becomes the root, and the rotating tree with root R to left, and then similarly W will, because W has already, with first rotation W will come here, and next will become the child of this W, but in the second rotation W will go up and R will come here. This is because the total height here is because one of the T2 or 3 has height h, so total height is h plus 3. In this case height is h plus 2. The first rotation and second rotation, the new balance factor of R and X depend on the previous balance factor from W. Now show the linked representation of the following 2 polynomials. Linked representation. This is the first one, this is the second one. These are the polynomials. So it will be like this. This is 7. This is what? This is the coefficient, or rather you can say a constant. Okay, 80 is the power, so 80 will write here. Then we go to the next one. So 5 will come here, 50 will come here. Next is 3 and 30 is 3. This is 30. Sorry, this is 30. So we make it. We change here. There is a slight change, 30, and then 1, and the power is 0, and then you have done. And polynomial 2 can be represented in a similar way. 9 will come here, 90 will come here, 6 come here, 60 will take place here, 2 will find its position here, 20 the power will come here, 1 will come here, that is minus 1, and 0 of course there is no power, so you have none here. So the node of the polynomial is of the form coefficient of the term, power of the x, and link to the next node. So we have three parts. So this is again some questions on data structure and algorithm. We'll be seeing more. Thank you so much. Take care.